Welcome back to Whispering Universes, where we explore the deepest questions about our place in the cosmos and the mysteries written in stone beneath our feet. Tonight, we're going to consider a question that might seem like science fiction, but is rooted in genuine scientific inquiry. A question that challenges our understanding of human uniqueness and forces us to confront the vast, almost incomprehensible timescales across which our planet has existed. What if we're not the first industrial civilization to arise on Earth? What if, millions or even hundreds of millions of years before the first human walked upright, another species developed technology, built cities, and left their mark on this world, only to have nearly every trace of their existence erased by the patient, inexorable processes of geology? This isn't idle speculation or ancient astronaut pseudoscience. This is a legitimate scientific question that emerged from a conversation between two serious researchers who wondered whether we would even be able to detect the signatures of an ancient industrial civilization in Earth's geological record. The answer, as we'll explore tonight, is far from obvious. The question opens a window into deep time, that vertiginous span of millions and billions of years that our minds struggle to grasp. And it reveals something profound about the nature of evidence, the limits of knowledge, and the fragility of everything we build. The Earth is approximately 4.5 billion years old. Complex multicellular life has existed for over 500 million years. Our species, Homo sapiens, has existed for perhaps 300,000 years, and we've had something resembling industrial civilization for less than 300 years. If you compressed Earth's entire history into a single year, with the planet forming at midnight on January 1st, modern humans wouldn't appear until 11:58 p.m. on December 31st, and industrial civilization would begin in the final fraction of a second before midnight. We are extraordinarily late to this planet's story. The vast majority of Earth's history unfolded without us, through ages dominated by creatures we can barely imagine, across climates and configurations of continents that bear little resemblance to the world we know. Within that immense span of time, could another species have developed technology, harnessed energy on a planetary scale, and then disappeared so completely that we have no direct evidence of their existence? Could the geological record, which seems so rich and informative when we study dinosaur fossils or ancient climates, actually be blind to the brief flourishing of technological civilizations? These questions touch something deep in our understanding of ourselves. We like to think of human civilization as unprecedented, a unique moment when matter became aware of itself and began to reshape the world according to its will. But deep time doesn't care about our self-importance. Deep time is patient, methodical, and incredibly good at erasing things. Tonight, here on Whispering Universes, we'll explore what scientists call the Silurian Hypothesis, named playfully after an intelligent reptilian species from the science fiction series Doctor Who. We'll examine what traces an industrial civilization actually leaves behind, how long those traces might persist, and what methods we could use to detect them millions of years later. We'll look at the chemistry of ancient rocks, the patterns of mass extinctions, and the strange thermal events preserved in ice cores and ocean sediments. We'll consider what our own civilization will leave behind for geologists of the far future, and we'll grapple with the uncomfortable reality that absence of evidence is not always evidence of absence. This journey will take us through 4.5 billion years of planetary history, from Earth's fiery birth, through the ages of bacteria and algae, through the explosion of complex life, through mass extinctions and ice ages, volcanic upheavals, and continental collisions, all the way to this present moment where you're listening to these words, perhaps drifting towards sleep, contemplating your connection to this impossibly ancient world. The question of whether we're first isn't just about other civilizations. It's about understanding what it means to exist in deep time, to be a brief pattern of complexity on a world that existed long before us and will exist long after, to build and create and think, while knowing that geology will eventually reclaim everything we make. Let the boundaries of time begin to soften now. Let your mind stretch backward across millions of years. We're going to explore the deepest history, the longest view, And in doing so, perhaps we'll see ourselves and our moment with new eyes. Before we can meaningfully ask whether another civilization existed in Earth's past, we need to develop some intuition for just how vast that past truly is. Deep time, the concept of geological ages spanning millions and billions of years, defies our everyday experience of temporal flow. Our brains evolved to track seasons, life cycles, and generations, not epochs and eras. We can understand intellectually that Earth is 4.5 billion years old, but we cannot truly feel what that means. The span is too large, the numbers too abstract. Yet, this incomprehensible vastness is precisely where the question of prior civilizations lives. Earth coalesced from the protoplanetary disk surrounding our young sun, approximately 4.54 billion years ago. For the first several hundred million years, the planet was hellish, frequently bombarded by asteroids and comets, its surface molten or barely solid, its atmosphere toxic and dense. The moon formed from debris ejected when a Mars-sized object called Theia collided with the early Earth around 4.5 billion years ago. Slowly, over hundreds of millions of years, the planet cooled. Oceans condensed from steam, the first solid crust formed, and was repeatedly melted and reformed by volcanism and impacts. By about 3.8 billion years ago, conditions had stabilized enough for liquid water to persist on the surface, and within a few 100 million years more, the first life emerged. For the next 3 billion years, Earth was a bacterial world. Single-celled organisms dominated the oceans, gradually transforming the atmosphere by producing oxygen as a waste product of photosynthesis. The Great Oxidation Event, around 2.4 billion years ago, fundamentally changed the planet's chemistry, filling the atmosphere with reactive oxygen and causing the first mass extinction of anaerobic bacteria. Eventually, some bacteria formed symbiotic relationships, merging to create the first complex cells with internal organelles. But for most of Earth's history, nothing visible to the naked eye existed. Just microscopic films of bacteria coating rocks and forming stromatolites in shallow seas. Complex multicellular life is a recent innovation, appearing only in the last 600 to 700 million years. The Ediacaran period, beginning around 635 million years ago, saw the first large, soft-bodied organisms, strange quilted creatures that don't clearly fit into any modern group. Then, around 541 million years ago, something remarkable happened. The Cambrian explosion brought a sudden diversification of animal life, with hard shells, jointed limbs, eyes, and predation all appearing in a geological instant. Within just a few tens of millions of years, most of the basic animal body plans we see today had evolved. From the Cambrian forward, Earth became recognizably alive in a modern sense. Fish evolved and colonized the oceans. Plants and arthropods moved onto land during the Ordovician and Silurian periods, around 450 to 400 million years ago. Forests appeared, followed by amphibians, then reptiles. The Carboniferous period, roughly 350 to 300 million years ago, saw vast swamp forests whose buried remains would become most of our coal deposits. Dinosaurs dominated from about 230 to 66 million years ago across the Triassic, Jurassic, and Cretaceous periods. Mammals existed alongside them as small creatures, waiting in the wings. Then, 66 million years ago, an asteroid struck the Yucatan Peninsula, ending the age of dinosaurs and opening ecological niches for mammals to expand and diversify. Primates evolved. The climate cooled into a series of ice ages. The first human ancestors appeared around 6 or 7 million years ago. Our species, Homo sapiens, evolved in Africa roughly 300,000 years ago. Agriculture began about 10,000 years ago. The Industrial Revolution started approximately 250 years ago. The computer age is measured in decades. When you place these timescales beside one another, a humbling picture emerges. Industrial civilization occupies 1/10,000th of 1% of Earth's history. The entire span of human existence represents less than 1/100th of 1%. We are an eye blink, a momentary flicker in an ancient story. This raises an obvious question. If intelligent, technological life could arise once in Earth's vast history, why couldn't it have arisen before? Not among humans, obviously, but among some other lineage, some species that flourished, built, thought, and then vanished before our ancestors even existed. The fossil record shows us that complex life has existed for over 500 million years. That's more than enough time for intelligence to evolve multiple times. The question isn't whether it's possible in principle, but whether we could detect it if it happened. To understand whether we could detect an ancient industrial civilization, we first need to understand what kinds of things the geological record actually preserves. The science of taphonomy, which studies how organisms decay and become fossilized, reveals that preservation is the exception, not the rule. The vast majority of living things leave no trace whatsoever. Their bodies decay, are consumed by other organisms, and their constituent atoms are recycled into new life. Only under very specific, unusual conditions does anything persist long enough to become a fossil, and even then, what remains is often fragmentary and distorted. Consider what happens to a typical animal when it dies. If it dies on dry land and isn't immediately buried, scavengers will consume the soft tissue within days or weeks. Bacteria and fungi will break down what remains. Bones may persist for years or decades if the environment is dry, but they too will eventually crumble, weathered by temperature changes, dissolved by acidic groundwater, or simply broken down by the endless work of bacteria. For fossilization to occur, the organism needs to be buried quickly in sediment, ideally in an oxygen-poor environment where decay proceeds slowly. The sediment protects the remains, while minerals gradually infiltrate and replace the original organic material, creating a stone replica of bone or shell, or very rarely, soft tissue. Even under ideal conditions, fossilization is extraordinarily unlikely. Paleontologists estimate that far less than 1% of all species that ever existed appear in the fossil record, and for most of those species, we have only a handful of fragmentary specimens. Soft-bodied organisms, which leave no hard parts to fossilize, are almost never preserved except in truly exceptional deposits like the Burgess Shale or the Chengjiang fauna, where unique chemical conditions allowed even muscles and internal organs to leave impressions in fine-grained sediment. These deposits are so rare that each one is considered a treasure trove of paleontological data. The problem compounds when we consider the time span involved. The fossil record does preserve organisms from hundreds of millions of years ago, but it does so with decreasing resolution as we look further back in time. Sedimentary rocks can be eroded, metamorphosed by heat and pressure, subducted into Earth's mantle at tectonic plate boundaries, or simply never formed in the first place in regions that weren't experiencing deposition. Large portions of Earth's history have poor fossil records simply because the rocks from those periods have been destroyed or so transformed that any fossils they contained are unrecognizable. The further back you look, the more gaps appear. Now consider what an industrial civilization leaves behind. Buildings, roads, machines, electronic devices, books, artwork. All the things we consider the obvious evidence of our existence are made of materials that decay relatively quickly on geological timescales. Wood rots in decades to centuries. Steel corrodes in centuries to millennia. Concrete crumbles as water infiltrates, and freeze-thaw cycles break it apart. Within a few tens of thousands of years after humans disappeared, even our largest structures would be reduced to scattered, weathered ruins, barely distinguishable from natural rock formations. Within a few 100,000 years, subduction zones would have started pulling some of our remains into Earth's mantle. Within a few million years, ice ages would have scoured continents, rivers would have carved new valleys, and plate tectonics would have rearranged coastlines. What about deliberate artifacts? The golden records we attach to the Voyager spacecraft are designed to last billions of years in the vacuum of space. But they're in space precisely because Earth's environment is so destructive. Any similar artifact buried on Earth would face groundwater, tectonic activity, and the slow but relentless chemical reactions that break down even the most stable materials. Some substances would persist longer than others. Certain ceramics might survive for millions of years, and we'll discuss plastics shortly. But these would exist as scattered fragments mixed into sedimentary layers, not as recognizable technological artifacts. The fossil record gives us dinosaur bones from 100 million years ago, because bone, once fossilized, is essentially rock, and rocks can persist for billions of years if they're not destroyed by tectonic processes. But a fossilized bone looks nothing like a living bone. It's a stone replica, a cast where minerals filled the spaces left by decayed organic material. An industrial artifact wouldn't fossilize in the same way. There's no biological template for minerals to replace. Instead, metals would corrode into rust or other oxide compounds. Synthetic materials would slowly break down into unrecognizable residues, and the complex shapes and structures that screamed technology would collapse into ambiguous fragments. This creates a profound challenge for detecting ancient civilizations. If nearly all direct physical evidence would vanish within a few million years, and if the gaps in the fossil record mean we might simply have no rocks from the relevant period or location, then we cannot rely on finding ruined cities or artifacts. We need to look for something more subtle, more persistent, something that could survive the processes that destroy everything else. We need to look for chemical signatures, isotopic anomalies, and patterns in the geological record that shouldn't exist if Earth's history included only natural processes. We need to learn to read messages written in stone and ice, messages that might be there, but that we don't yet know how to interpret. Let's imagine a thought experiment that brings this question into sharper focus. Suppose humanity disappeared tomorrow, not in a catastrophic explosion, but simply vanished, leaving all our buildings, roads, artifacts, and technological infrastructure exactly as they are right now. How long would evidence of our civilization remain detectable? The answer depends on what you're looking for and how carefully you're searching. But the timeline is surprisingly short when measured against geological time. In the first few years after our disappearance, nature would begin reclaiming the landscape with remarkable speed. Plants would colonize roads and sidewalks, growing through cracks and breaking up pavement. Without maintenance, buildings would begin to leak, and water damage would accelerate their decay. Wooden structures would rot within decades in humid climates. Glass windows would shatter from storms or temperature stress. Metal would start to corrode, especially in coastal areas where salt spray accelerates oxidation. Animals would move into our abandoned cities, nesting in our homes and offices, spreading organic matter that would support further plant growth. Within a few hundred years, most houses would have collapsed. Skyscrapers might remain standing longer, their steel and concrete frames more resistant to immediate decay, but even these would begin to show serious damage. Water infiltration would cause steel reinforcing bars to rust and expand, cracking the concrete around them. Freeze-thaw cycles in temperate climates would accelerate this process. Glass facades would have fallen away, and floors would have collapsed as wooden or metal supports gave way. Cities would become overgrown ruins, recognizable in their basic layout, but already merging back into the landscape. After 1,000 years, very little would remain above ground. Some structures built of stone might persist as recognizable ruins. Pyramids and monuments made of granite or limestone could last tens or hundreds of thousands of years, similar to natural rock formations. But the vast majority of our built environment would be gone. Roads would be completely overgrown, their asphalt and concrete broken into fragments and scattered by frost heave and root growth. Suburbs would be forest or grassland again, with no visible trace of the houses that once stood there. Cities would be low mounds of rubble, gradually being eroded by wind and rain. Now accelerate forward to 10,000 years, approximately the time since agriculture began, but running backward from our disappearance. Ice ages would have advanced and retreated if we're in the right part of Earth's orbital cycle. Glaciers would have scraped across northern continents, removing even the foundations of cities and grinding everything into fine sediment. River valleys would have shifted course, carving through ancient urban zones and carrying away any remaining fragments. The landscape would look entirely natural to any observer. A few scattered anomalies might exist, unusually high concentrations of certain materials in sediment layers, strange chemical compositions in soil that once was pavement. Perhaps a handful of the most durable artifacts like certain ceramics or glass objects weathered beyond recognition. At 100,000 years, even those traces would be almost entirely gone from the surface. The only evidence would be in the geological record itself. Subtle anomalies in sedimentary layers, chemical signatures in rocks that happen to be forming during our industrial period, changes in isotope ratios in ice cores, if any ice from our era survived. At 1 million years, direct artifacts would be essentially impossible to find. You would need to know exactly where to look and exactly what chemical or isotopic signatures to search for. At 10 million years, even that would be challenging. Plate tectonics would have moved continents measurably. Subduction zones would have consumed seafloor that existed during our time. Mountain ranges would have risen or eroded. The geological record from our period might be buried under kilometers of newer rock, or it might have been destroyed entirely by metamorphism or erosion. This timescale is crucial for understanding the Silurian hypothesis. If humanity's entire industrial civilization, with 8 billion people, global cities, roads, mines, factories, and an atmosphere measurably altered by our activity, could become essentially undetectable within 10 million years, then any previous industrial civilization would face the same challenge. 10 million years is a long time by human standards, longer than our species has existed by a factor of more than 30, but it's a short time geologically. It's only 0.2% of the time since complex animal life appeared in the Cambrian. It's a thin slice of deep time, and the fossil record routinely has gaps longer than that, simply because no rocks were being formed in particular regions during particular periods, or because the rocks that did form have since been destroyed. The thought experiment reveals something profound. Civilizations have a kind of half-life, a characteristic timescale over which their direct evidence decays away. For most of what we build, that half-life is measured in decades to centuries. For our most durable structures, it might extend to tens of thousands of years. For any trace of our existence to persist into the deep geological future, it must be encoded in the rocks themselves, in chemistry and isotopes, not in artifacts and ruins. This is what makes the search for prior civilizations so challenging and so fascinating. We're not looking for alien pyramids or ancient highways. We're looking for whispers in stone, subtle anomalies that might indicate a temporary pulse of industrial activity in Earth's ancient past. Anomalies that might be there, but that we wouldn't recognize unless we knew to look for them. The geological record is Earth's memory, written in layers of sediment and preserved in ancient rocks. Geologists are the translators of this memory, reading the story of our planets, passed from the physical and chemical evidence locked in stone. To understand whether we could detect an ancient industrial civilization, we need to understand what information rocks actually contain and how precisely we can read it. The answer is complex. Geology reveals some things with remarkable clarity, while leaving other questions completely unanswerable. The resolution with which we can examine Earth's past varies dramatically depending on how far back we look and what kind of evidence we're seeking. Sedimentary rocks form when particles of sand, silt, clay, or organic matter settle out of water or air and gradually compact and cement together over thousands to millions of years. Each layer represents a period of deposition, and the sequence of layers, called stratigraphy, provides a timeline of geological events. By examining the type of sediment, its grain size, the fossils it contains, and its chemical composition, geologists can reconstruct ancient environments with impressive detail. They can tell whether a particular layer was deposited in a shallow ocean, a deep ocean basin, a river delta, a lake, or on dry land. They can determine whether the climate was warm or cold, wet or dry. They can track the opening and closing of ocean basins as continents drift, the rise and fall of mountain ranges, and the advance and retreat of ice sheets. Chemical analysis of sedimentary rocks provides even more information. The ratios of different oxygen isotopes in calcium carbonate fossils reveal ancient ocean temperatures. Carbon isotopes tell us about photosynthetic activity and the carbon cycle. Sulfur isotopes record volcanic activity and oxidation states. Trace elements provide clues about ocean chemistry, weathering rates on land, and biological productivity. Modern analytical techniques can measure these isotopic ratios with extraordinary precision, detecting changes that occurred over periods of just a few thousand years, or sometimes less, depending on the sedimentation rate. But this precision comes with significant limitations. First, not all time periods have equally good geological records. Rock formation requires specific conditions, areas where sediment accumulates and is buried rather than eroded away. Seafloors near continental margins are excellent for this, creating thick sequences of marine sediment that preserve long, continuous records. Continental interiors are more problematic, with rivers cutting through existing rock and removing evidence of past conditions. Old rocks are preferentially destroyed by tectonic activity, metamorphism, and erosion, so the further back in time you look, the patchier the record becomes. Large portions of Earth's surface have no exposed rocks, older than a few 100 million years, not because nothing happened during earlier periods, but because those rocks have been destroyed or buried. Second, the temporal resolution of the geological record varies dramatically. In ideal circumstances, with fine-grained sediment deposited continuously at high rates, geologists can distinguish individual years or even seasons. Varves, annual layers in lake sediments analogous to tree rings, provide this kind of precision for certain locations and time periods, but these circumstances are rare. More commonly, a single layer of sediment represents hundreds or thousands of years of accumulation. Unconformities, gaps in the rock record, where either deposition stopped or erosion removed existing rock, can represent millions of years of missing time. When examining ancient rocks, geologists often work with resolution measured in tens or hundreds of thousands of years, sometimes longer. This variable resolution creates a detection problem for ancient civilizations. If an industrial civilization arose, flourished for a few thousand years, and then disappeared, its influence on the planet would be compressed into an extremely thin stratigraphic layer, possibly too thin to sample separately from the layers above and below it. Imagine trying to find a 1 centimeter band of unusual chemistry in a rock formation hundreds of meters thick, where that 1 centimeter band represents the entire span of the civilization's industrial period. Unless you had reason to suspect something unusual and looked very carefully, you might simply miss it. The signal could be there, preserved in the rock, but diluted or averaged out with the surrounding material. Third, not all events leave clear signatures. A civilization mining coal or drilling for oil would redistribute elements and isotopes, but would those changes be distinguishable from natural processes millions of years later? A civilization releasing carbon dioxide and other greenhouse gases would alter atmospheric composition and potentially trigger climate change. But Earth's climate has changed dramatically many times for natural reasons, driven by volcanism, orbital variations, asteroid impacts, and the evolution of photosynthetic organisms. Distinguishing an anthropogenic signal from natural variability requires very careful analysis and often leaves room for multiple interpretations. Despite these challenges, geology has proven remarkably powerful at detecting transient events in Earth's past. The asteroid impact that ended the Cretaceous period 66 million years ago left a clear signature: a thin layer of clay enriched in iridium, an element rare on Earth's surface but common in asteroids, found at the same stratigraphic level all over the world. Ancient volcanic eruptions are recorded in ash layers, their chemical fingerprints allowing geologists to correlate distant locations and establish precise timelines. The oxygen isotope record in ocean sediments reveals every ice age of the past few million years with extraordinary clarity. If an industrial civilization left sufficiently unusual chemical or isotopic signatures, geology should be able to find them, even millions of years later, provided we know what to look for and have rocks from the right time and place to examine. This is the fundamental challenge. The geological record is a powerful tool, but it requires us to ask the right questions and look in the right places with the right techniques. The question of whether we're the first civilization Earth has produced isn't one that traditional geology was designed to answer. We need to think carefully about what signatures an industrial civilization would leave, and whether those signatures would be distinguishable from natural phenomena. We need to be open to the possibility that we've already found anomalies in the geological record and simply interpreted them as natural events because we had no reason to consider an alternative explanation. The term Silurian Hypothesis first appeared in a 2018 paper by Gavin Schmidt, director of NASA's Goddard Institute for Space Studies, and Adam Frank, an astrophysicist at the University of Rochester. The name is borrowed from Doctor Who, the long-running British science fiction series featuring a reptilian species called the Silurians, who evolved intelligence on Earth millions of years before humans and built an advanced civilization before going into hibernation underground. Schmidt and Frank chose the name playfully, but their question was serious. If an industrial civilization had existed on Earth millions of years ago, how would we know? What evidence would remain, and how would we detect it? The paper emerged from a conversation about detecting industrial civilizations on other planets. Frank was working on questions about whether we could observe technological activity on exoplanets by looking for chemical signatures in their atmospheres, signs of artificial structures, or anomalies in their reflected light. Schmidt, as a climate scientist, thought carefully about how industrial activity affects planetary systems. During their discussion, someone raised an interesting question. If we're trying to figure out how to detect alien industrial civilizations on distant planets, shouldn't we first establish whether we could detect such a civilization if it had existed on Earth in the geological past? After all, we have direct access to Earth's geological record in a way we'll never have for exoplanets. Earth is the test case. When they started examining the question seriously, Schmidt and Frank realized that the answer wasn't obvious at all. In fact, the more they thought about it, the more challenging the detection problem appeared. They weren't arguing that prior industrial civilizations actually existed on Earth, and they weren't promoting any kind of ancient astronaut pseudoscience. Instead, they were asking a methodological question. Given what we know about geology, paleontology, and the preservation of evidence in deep time, what traces would we expect to find if a civilization like ours had existed 50 million years ago, or 100 million years ago, or even longer? And critically, would we have already found those traces if they existed? Or might they be sitting in the geological record, waiting for someone to ask the right question? The thought experiment forced them to confront the limits of the fossil record. Humans have been anatomically modern for perhaps 300,000 years, but we've been industrial for only about 250 years. And our impact on the planet has been most intense only in the last 70 years, the period sometimes called the Great Acceleration. This means that the ratio of our total existence to our industrial period is about 1,000 to 1, and the ratio of our industrial period to the age of the Earth is about 1 to 18 million. Our industrial civilization is an incredibly brief pulse, a moment of intense activity on a planet that has existed for billions of years. If some other species had experienced a similar transition, say 60 million years ago during the early Paleocene, their industrial pulse would be equally brief relative to Earth's history, and it would be compressed into an extremely thin stratigraphic layer, possibly only a few centimeters thick in sedimentary rocks deposited over millions of years. Schmidt and Frank identified several potential signatures that an industrial civilization might leave in the geological record. Some are chemical: changes in the carbon cycle from burning fossil fuels, nitrogen cycle disruption from agriculture and industry, elevated concentrations of rare earth elements from mining and technological processes, and the presence of synthetic molecules that don't occur naturally. Some are isotopic: shifts in the ratio of carbon-12 to carbon-13 from burning coal and oil, which preferentially releases the lighter isotope, or the presence of artificial radioisotopes from nuclear technology. Some are biological: rapid extinction events or changes in the distribution of species driven by habitat, destruction, and climate change rather than natural causes. The key insight was that many of these signatures would look similar to natural events. Earth has experienced rapid climate changes before, driven by massive volcanic eruptions or the release of methane from ocean sediments. The carbon isotope ratio has shifted naturally during these events because biological carbon has a different isotopic signature than inorganic carbon. Mass extinctions have occurred multiple times, caused by asteroid impacts, volcanism, or environmental changes. Rare earth elements are concentrated in certain geological formations naturally. The challenge isn't whether an industrial civilization would leave traces. It's whether those traces would be distinguishable from the background of natural variability that characterizes Earth's geological history. This is where the Silurian Hypothesis becomes genuinely interesting as a scientific question. It's not really about whether aliens or dinosaurs built cities and then vanished. It's about the philosophy of evidence and the limits of what we can know about deep time. It forces us to think carefully about how we interpret the geological record and whether our interpretations are complete or whether we might be missing signals simply because we haven't thought to look for them. It encourages us to develop better methods for detecting transient, unusual events in Earth's past, methods that might also help us understand our own civilization's impacts and how they'll appear to geologists millions of years in the future. The hypothesis also has implications for astrobiology. If we struggle to detect even a hypothetical prior civilization on our own planet, where we have direct access to rocks and can sample them with arbitrary precision, how much more difficult would it be to detect technological life on an exoplanet, where we're limited to analyzing light filtered through an atmosphere or reflecting off a surface? The question humbles us. It reminds us that absence of evidence is not the same as evidence of absence, especially when dealing with timescales and distances that dwarf human experience. It suggests that the universe might hide its secrets more effectively than we'd like to believe, and that intelligence, even industrial intelligence, might be more difficult to detect than popular science fiction would suggest. Before we can meaningfully search for evidence of prior industrial civilizations, we need to define what we mean by that term. Not all civilizations would leave the same traces, and not all intelligent species would necessarily develop technology or alter their environment in detectable ways. The question of what constitutes an industrial civilization isn't purely semantic. It shapes what we look for and where we expect to find it. Human civilization provides the only example we have, but we need to think carefully about which aspects are likely to be universal and which might be unique to our particular history and biology. At the most basic level, an industrial civilization is one that harnesses energy on a large scale to transform raw materials and reshape its environment. Energy use is perhaps the most fundamental marker. Pre-industrial human societies used primarily biological energy, the calories in food, and the muscle power of animals, supplemented by relatively small amounts of energy from burning wood, harnessing wind and water, and manipulating fire. The Industrial Revolution marked a transition to fossil fuel energy, coal first, and then petroleum and natural gas, which provided vastly more power and enabled the development of machines, factories, transportation networks, and eventually electrical grids that could deliver energy wherever it was needed. This energy transition is probably necessary for any industrial civilization, though the specific energy source might vary. A civilization might harness geothermal energy, tidal energy, nuclear fission or fusion, or even biological systems engineered to produce energy more efficiently than natural photosynthesis. But fundamentally, industrialization means accessing energy reserves beyond what biological metabolism alone can provide, and doing so at a scale that affects the planetary environment. Our civilization's energy use has increased by orders of magnitude over the past 2 centuries, and that increase has left clear signatures: carbon dioxide and methane in the atmosphere, nitrogen oxides from combustion, particulate pollution, thermal pollution of waterways, and the physical infrastructure of mines, power plants, and distribution networks. A second defining characteristic of industrial civilization is the manipulation of materials and the creation of synthetic substances. We mine metals, refine ores, synthesize polymers, and create alloys and compounds that don't occur naturally or don't occur in the concentrations and forms we need. This material transformation is visible in the geological record as chemical anomalies. Elevated concentrations of certain elements in sediments, unusual isotopic ratios from industrial processes, and the presence of entirely synthetic molecules like plastics, pesticides, and industrial chemicals. Any industrial civilization would presumably need to manipulate materials in similar ways, creating chemical signatures that might persist long after the civilization itself disappeared. A third characteristic is agriculture, or some equivalent system for producing food at scales beyond what hunting and gathering can support. Industrial civilizations require large populations, and large populations require reliable food surpluses. Human agriculture has profoundly altered Earth's surface, with roughly 38% of ice-free land now used for crops or pasture. This land use change affects soil chemistry, erosion rates, and the distribution of plant and animal species. We've also altered the nitrogen cycle through the industrial production of fertilizers, roughly doubling the amount of reactive nitrogen available to organisms. These changes would leave signatures: shifts in pollen records preserved in sediments, changes in erosion rates and sediment deposition patterns, and alterations to the nitrogen isotope ratios in soils and sediments. A fourth characteristic might be urbanization, the concentration of populations in cities. Cities represent intense local alteration of the environment. Natural landscapes replaced with built structures, local climates modified by the heat island effect, water drainage patterns completely changed, and ecosystems either destroyed or radically simplified. Cities also create waste disposal problems, leading to landfills and other concentrated deposits of unusual materials. However, urbanization might be less universal than energy use or material manipulation. A civilization could potentially be industrial without large cities if their technology or social structure was organized differently. Still, concentration of activity probably creates more detectable signatures than diffuse low-level impacts across wide areas. Finally, we should consider whether industrial civilization necessarily implies negative environmental impacts. Our civilization's impacts include climate change, ocean acidification, the sixth mass extinction, pollution of air and water, and the degradation of ecosystems worldwide. But are these consequences inevitable, or could a different kind of industrial civilization develop in harmony with its environment? Perhaps a species with different values or longer lifespans might prioritize sustainability from the beginning. Perhaps their biology would lead them to integrate technology with natural systems, rather than replacing nature with artificial ones. However, thermodynamics suggests that any large-scale energy use creates waste heat and entropy, and any large-scale manipulation of materials generates byproducts and altered chemical cycles. Some environmental footprint seems unavoidable for industrial activity, even if its specific character might vary. For the purposes of the Silurian hypothesis, we're primarily interested in civilizations that would leave detectable signatures in the geological record. This probably biases us towards civilizations with significant environmental impacts, since those impacts are precisely what creates the chemical and isotopic anomalies we might detect millions of years later. A perfectly sustainable civilization that left no trace might have existed, but we would have no way to know. This creates a kind of observational selection effect. We can only search for civilizations that were, in some sense, geologically visible. It's a humbling limitation, reminding us that our search is necessarily incomplete, constrained by the nature of evidence itself. As you consider these definitions, let your mind drift across the possibilities. Imagine species very different from us, with different biologies and different needs, developing their own forms of industry. Imagine what traces they might leave, what signatures might persist across millions of years. The question expands beyond simple yes or no. It becomes a meditation on the nature of intelligence, the relationship between technology and environment, and the deep patterns that might govern how complex life interacts with planetary systems. If we cannot find direct artifacts from a prior industrial civilization, we must look for more subtle evidence. Chemical and isotopic anomalies in ancient sedimentary rocks that might indicate transient periods of unusual activity. Modern analytical techniques allow geochemists to measure the elemental and isotopic composition of rocks with extraordinary precision, detecting shifts and patterns that reveal ancient environmental conditions. The question is whether these techniques could distinguish between natural variations and those caused by industrial activity, and whether any such signatures would survive the processes that transform and sometimes destroy sedimentary rocks over millions of years. Carbon isotopes provide one of the most promising potential signatures. Carbon exists in two stable isotopes, carbon-12, the lighter and more common form, and carbon-13, which is about 1.1% heavier. Photosynthetic organisms preferentially incorporate carbon-12 into their tissues because lighter molecules diffuse and react slightly more readily, creating a small but measurable isotopic fractionation. When we burn fossil fuels, coal, oil, and natural gas derived from ancient photosynthetic organisms, we release carbon that is enriched in carbon-12 relative to the average for Earth's surface. This shifts the ratio of carbon-12 to carbon-13 inches, the atmosphere, and eventually in ocean water and sediments. The shift is small but detectable. Atmospheric carbon dioxide measurements show that the carbon-13 to carbon-12 ratio has been decreasing steadily since the Industrial Revolution, and this change is preserved in tree rings, ice cores, and marine sediments. The question is whether the signal would remain clear over millions of years, or whether later geological processes might obscure it. The challenge is that carbon isotope ratios naturally vary in sedimentary rocks for many reasons. Large volcanic eruptions release carbon dioxide from Earth's mantle, which has a different isotopic composition than surface carbon. The burial and weathering of organic carbon affects the ratios in ocean water. Changes in ocean circulation or the productivity of marine ecosystems create shifts. Most dramatically, several periods in Earth's history show rapid negative excursions in carbon isotopes, events where the carbon-13 to carbon-12 ratio dropped quickly and then recovered. The most famous is the Paleocene-Eocene thermal maximum about 56 million years ago, where massive amounts of isotopically light carbon entered the atmosphere and oceans, causing rapid global warming. Scientists still debate what caused the PETM. The most likely explanation involves the destabilization of methane hydrates, frozen deposits of methane in ocean sediments that melted when ocean temperatures rose past a critical threshold, releasing vast amounts of greenhouse gas in a runaway feedback loop. But the carbon isotope signature looks similar to what an industrial civilization burning fossil fuels would create. Without other evidence, could we distinguish between these scenarios? Perhaps, if we could examine the rate of change and the spatial distribution of the anomaly. But the time resolution in rocks this old is often not precise enough for such detailed analysis. Nitrogen isotopes offer another potential marker. The natural nitrogen cycle involves the conversion of atmospheric nitrogen into biologically useful forms through the action of nitrogen-fixing bacteria, followed by various transformations, and eventually the return of nitrogen to the atmosphere through denitrification. Industrial civilization has massively perturbed this cycle through the Haber-Bosch process, which synthesizes ammonia from atmospheric nitrogen for use in fertilizers. This industrially fixed nitrogen has a slightly different isotopic signature than biologically fixed nitrogen, and the huge increase in reactive nitrogen availability has altered nitrogen isotope ratios in soils, rivers, and coastal marine sediments. Again, the challenge is distinguishing this from natural variations. Nitrogen isotopes in ancient rocks vary for many reasons. Changes in ocean oxygenation, variations in biological productivity, volcanic inputs, and the weathering of continental rocks all create isotopic shifts. An industrial nitrogen pulse would need to be unusually large and rapid to stand out from this background variability, and we would need to have good sedimentary records with high temporal resolution from the right time period. Heavy metals and rare earth elements present another possibility. Industrial mining and refining concentrate these elements and redistribute them in unusual ways. Lead from leaded gasoline, mercury from coal combustion, platinum group elements from catalytic converters. All of these appear in sediments at elevated concentrations starting in the mid-20th century. Rare earth elements used in electronics and specialized alloys are found in higher concentrations in industrial waste streams than in natural rocks. If a prior civilization mined and processed these elements, they might have left similar concentration anomalies in sediments. The persistence of these signatures depends on the specific element and the geological environment. Some elements are relatively immobile in sediments, remaining where they were originally deposited for hundreds of millions of years. Others are easily remobilized by groundwater or chemical reactions, migrating through rock formations and potentially erasing their original distribution patterns. Lead isotopes offer an interesting case. Different ore deposits have different isotopic signatures because they formed at different times in Earth's history. So the pattern of lead isotopes in sediments can sometimes reveal where the lead came from, distinguishing natural weathering from anthropogenic redistribution. Finally, we should consider entirely synthetic molecules, compounds that don't occur naturally at all, and whose presence would unambiguously indicate technological activity. Plastics are the obvious example for our civilization, but we'll devote an entire chapter to them shortly. Other candidates include certain pesticides, industrial solvents, and pharmaceutical compounds. The challenge is that complex organic molecules typically break down over thousands to tens of thousands of years through oxidation, photolysis, and bacterial degradation. By the time millions of years have passed, most organic compounds will have been completely destroyed. Only if a synthetic molecule happened to be extremely stable and was deposited in very favorable preservation conditions, perhaps in deep ocean sediments with low oxygen levels, might fragments persist long enough to be detected in ancient rocks. These chemical signatures offer our best hope for detecting a prior industrial civilization, but they demand that we look carefully, that we develop comprehensive baseline data about natural variability, and that we remain open to multiple interpretations. An anomaly in the isotopic record is just that, an anomaly, until we can demonstrate that it exceeds the range of natural variation and matches what we would expect from industrial activity. This is difficult, humbling work, requiring patience, precision, and the willingness to accept that some questions might remain genuinely unanswerable. Among all the materials our civilization has created, plastics stand out as perhaps the most distinctive and potentially long-lasting signature. Since the development of synthetic polymers in the early 20th century, and especially since the explosion of plastic production after World War II, we've created an entirely new class of materials that barely existed before, and that will persist in the environment for timescales that dwarf our own civilization's age. Plastics are already accumulating in sediments worldwide, creating what future geologists might recognize as a unique stratigraphic marker, a thin layer of synthetic polymers that appears suddenly in the geological record and could potentially remain detectable for millions of years. The scale of plastic production is staggering. Humanity has produced over 8 billion metric tons of plastic since 1950, with production accelerating dramatically in recent decades. Much of this plastic ends up in the environment rather than being recycled or properly disposed of. Plastic debris accumulates in oceans, carried by currents into vast gyres, where it concentrates into garbage patches. Microplastics, tiny fragments broken down from larger pieces by sunlight and wave action, are now found throughout marine and freshwater ecosystems, in soils, in the atmosphere, and even in human bodies. Every marine sediment core taken from the deep ocean floor shows a sharp increase in plastic particles, starting around 1,950, creating a clear marker horizon. What makes plastics potentially persistent is their chemical stability. Most synthetic polymers are hydrocarbons, long chains of carbon and hydrogen atoms, similar in some ways to natural organic molecules, but with much more regular structure and often with chemical modifications that make them resistant to degradation. Natural enzymes evolved to break down plant and animal tissues don't work efficiently on synthetic polymers. Bacteria and fungi that normally decompose organic matter struggle with plastics because the molecular structures are unfamiliar. Photodegradation from ultraviolet light can break down plastics at the surface, but once buried in sediment where sunlight cannot penetrate, plastic fragments can persist indefinitely. Laboratory studies and observations of plastic in the environment suggest that while plastics do eventually degrade, the process takes centuries to millennia, depending on the polymer type and environmental conditions. Polyethylene and polypropylene, the most common plastics, break down more readily than polyvinyl chloride or polyethylene terephthalate. But even in the most favorable degradation conditions, warm temperatures, exposure to sunlight, mechanical abrasion, and active microbial communities, plastics last far longer than natural organic materials. In the deep ocean sediments where temperatures are near freezing, oxygen is limited, and sunlight never reaches, plastic fragments might persist for millions of years with little chemical change. This persistence creates a unique marker for our geological period. Future geologists, studying rock layers from the early 21st century, would find a sudden appearance of small particles with unmistakable characteristics, polymer chains with regular molecular structure, often containing additives like plasticizers or flame retardants, sometimes with characteristic shapes indicating manufactured origin. These particles would be globally distributed, appearing in marine sediments on every continent, in lake deposits, in soils, anywhere sediment was accumulating during our industrial period. The distribution pattern itself would be informative, with higher concentrations near coastlines and in regions affected by ocean currents. Some scientists have proposed calling our current geological epoch the Plasticine, or using plastics as one of the defining markers of the Anthropocene. The proposed new epoch, characterized by human modification of Earth's systems. The advantage of plastics as a stratigraphic marker is that they appear suddenly, persist widely, and have a clearly artificial origin. Unlike changes in carbon isotopes or extinction patterns, which might have multiple possible causes, the presence of synthetic polymers in sediments can only mean one thing: technological activity that included organic chemistry sophisticated enough to synthesize and mass-produce complex molecules. Now consider what this means for the Silurian hypothesis. If a prior industrial civilization developed organic chemistry and created synthetic materials analogous to our plastics, those materials might still be detectable in sedimentary rocks millions of years old. We would be looking for organic molecules with unusual structures, perhaps long-chain hydrocarbons, with regular branching patterns unlike any natural polymer, or molecules containing elements or functional groups in combinations that don't occur biologically. The challenge is that we typically don't analyze ancient rocks with this question in mind. Organic geochemistry usually focuses on biomarkers, molecules derived from ancient organisms that help us understand past ecosystems and that petroleum geologists use to characterize oil and gas deposits. The techniques aren't optimized for detecting small amounts of synthetic polymers mixed into organic-rich sediments. There's another challenge. Even synthetic polymers eventually degrade on timescales of millions of years. While plastics are extraordinarily stable compared to natural organic matter, they're not completely inert. Very slow oxidation, very slow hydrolysis, and reactions with other chemicals in sediments would gradually break down polymer chains, especially as rocks are buried deeper and experience elevated temperatures and pressures. After tens of millions of years, the original plastic particles might be gone, broken down into smaller organic molecules or even fully mineralized. But the byproducts of their degradation might persist. Unusual distributions of organic compounds, strange molecular fragments, or carbon-rich deposits with isotopic signatures that don't match normal biological material. The plastic stratum forming in today's sediments will tell future geologists something important about our civilization. We created new materials on a global scale. We did so in an extraordinarily brief period, geologically speaking, and we distributed those materials through environmental pathways that carried them everywhere. It's a marker of technological sophistication, global reach, and perhaps of carelessness or short-term thinking. If we find something analogous in ancient rocks, a layer with unusual synthetic compounds appearing suddenly and distributed widely, it would be strong evidence for a prior civilization. But the absence of such a layer wouldn't prove such a civilization never existed. They might have used different materials, or their synthetic compounds might have degraded more completely, or we simply haven't looked in the right rocks with the right analytical techniques. The search continues, patient and methodical, reading the chemical language written in stone. The development of nuclear technology represents one of humanity's most profound technological achievements and creates some of the most unambiguous signatures that might persist in the geological record far into the future. Nuclear fission and fusion produce isotopes that don't occur naturally in significant quantities, and some of these isotopes have half-lives long enough that they could remain detectable millions of years after they were created. If a prior industrial civilization developed nuclear technology, they might have left similar radioactive traces, though finding and interpreting those traces presents unique challenges. Our civilization's nuclear signature began with the Trinity test in July 1945, the first detonation of a nuclear weapon. The subsequent decades of atmospheric nuclear testing, from 1945 to 1980, when most testing moved underground, released enormous quantities of radioactive material into the atmosphere. These materials circulated globally before settling out into soils, lakes, and ocean sediments, creating a clear stratigraphic marker that geologists have proposed as the boundary definition for the Anthropocene. The marker is visible worldwide in sediment cores, ice cores, and even tree rings. A sharp spike in radioactivity, beginning in the mid-1940s and peaking in the early 1960s before the Partial Nuclear Test Ban Treaty reduced atmospheric testing. The most commonly used marker isotope is plutonium-239, which has a half-life of about 24,000 years. Plutonium-239 does not occur naturally on Earth's surface in measurable quantities, because any primordial plutonium that existed when Earth formed has long since decayed away. Plutonium's half-life is short compared to the age of the solar system. Finding plutonium-239 inches modern sediments is unambiguous evidence of nuclear technology, specifically either weapons testing or accidents at nuclear facilities. Other artificial isotopes include plutonium-240, cesium-137, with a half-life of 30 years, strontium-90, with a half-life of 29 years, and various isotopes of americium and curium. The problem with using these isotopes to detect ancient civilizations is their relatively short half-lives. After 10 half-lives, a radioactive isotope has decayed to about 1,000th of its original quantity, making it very difficult to detect. Plutonium-239, the longest-lived common isotope from nuclear weapons, would be reduced to undetectable levels after about 240,000 years, less than the time modern humans have existed. Looking for plutonium or fission products in rocks millions of years old would be pointless. Any isotopes from a prior civilization's nuclear age would have completely decayed. However, some other nuclear signatures might persist longer. If a civilization used nuclear reactors extensively for power generation, they would have produced substantial quantities of certain transuranic elements. Some isotopes of neptunium have half-lives exceeding 2 million years. Technetium-99 has a half-life of 211,000 years. While these isotopes also exist naturally in tiny quantities produced by spontaneous fission of uranium in Earth's crust. An industrial nuclear program would create anomalously high concentrations that might be detectable for 1 million years or more if we knew exactly where to look. The challenge is that these isotopes would be diluted through geological processes mixed with surrounding sediment, and potentially mobilized by groundwater, making the original concentration spike very difficult to identify. An interesting comparison comes from the Oklo Natural Nuclear Reactor in Gabon, Africa. About 2 billion years ago, uranium ore deposits at Oklo had just the right combination of concentration, geometry, and water content to sustain natural fission chain reactions. These natural reactors operated intermittently for hundreds of thousands of years, generating heat and producing the same kinds of fission products that modern nuclear reactors create. Geologists discovered Oklo when they noticed anomalous isotope ratios in uranium ore from the mine. The uranium-235 to uranium-238 ratio was lower than expected, indicating that uranium-235 had been consumed by fission reactions. The Oklo discovery is remarkable for several reasons. First, it demonstrates that natural fission reactions can occur under the right conditions, meaning we need to be careful about interpreting any fission products we might find in ancient rocks. Second, it shows that fission product signatures can persist for billions of years, although in this case, heavily altered by geological processes and recognizable primarily through careful isotope ratio analysis rather than direct detection of short-lived fission products. Third, it reminds us that Earth contains surprises and that unusual geological phenomena can mimic aspects of technological activity. If a prior civilization used nuclear power extensively, might they have left anomalies similar to Oklo, but with a different pattern? Perhaps concentrations of elements that don't occur together naturally, or isotope ratios that can't be explained by natural fission reactions and neutron capture. This seems like a promising avenue for investigation, but it requires knowing what patterns to look for and having access to appropriate samples. Most rock sampling and analysis is done for other purposes: mining exploration, petroleum geology, or understanding Earth's natural history, and wouldn't necessarily identify subtle nuclear signatures, even if they existed. There's another intriguing possibility. A sufficiently advanced civilization might have developed fusion power, which leaves a very different signature than fission. Fusion reactions can produce certain light isotopes, particularly helium-3 and tritium, though tritium's extremely short half-life of about 12 years means it wouldn't persist. Helium-3 is stable and doesn't occur in large quantities naturally on Earth because it's produced primarily by cosmic ray interactions in the atmosphere and escapes to space. Earth's gravity isn't strong enough to retain helium efficiently. An industrial fusion program might create anomalous helium-3 concentrations, but detecting this in ancient rocks would be extraordinarily difficult because helium doesn't incorporate into minerals and tends to diffuse out of rocks over geological time. The nuclear signature is perhaps the most unambiguous potential marker of industrial civilization. Synthetic radioisotopes simply don't exist without nuclear technology. But it's also one of the most challenging to detect over millions of years because of radioactive decay and geological processes that disperse and obscure original concentrations. This creates an interesting asymmetry. Our civilization's nuclear age will be clearly detectable for tens of thousands of years, but invisible within a million years, while other signatures like plastics or carbon isotope shifts might persist much longer, even though they're less uniquely technological. The search for prior civilizations must contend with these varying timescales of evidence, accepting that different markers fade at different rates and that our window of detection is limited by the physics of decay and the geology of preservation. Earth's history includes several mass extinction events, periods when large percentages of species disappeared in geologically brief intervals. These extinctions are written clearly in the fossil record as major disruptions in the diversity and distribution of life, and their causes have been subjects of intense scientific investigation. As we consider whether industrial civilizations might leave detectable traces, we must ask an uncomfortable question. Could a technological civilization cause a mass extinction? And if so, would that extinction be distinguishable from those caused by natural phenomena like asteroid impacts or massive volcanic eruptions? The 5 largest mass extinctions in Earth's history, often called the Big Five, occurred at the end of the Ordovician, about 444 million years ago, in the late Devonian, about 375 million years ago, at the end of the Permian about 252 million years ago, at the end of the Triassic about 201 million years ago, and at the end of the Cretaceous 66 million years ago. Each eliminated between 50 and 96% of species, fundamentally restructuring ecosystems and opening ecological niches for survivor lineages to diversify and radiate into. The causes are varied and sometimes still debated, but they generally involve some combination of climate change, ocean chemistry changes, volcanic activity, and in the case of the end Cretaceous, a massive asteroid impact. Our civilization is currently driving what many biologists consider a 6th mass extinction. Species extinction rates are 100 to 1,000 times higher than background rates measured from the fossil record, and extinction risk is accelerating due to habitat destruction, climate change, pollution, overharvesting, and the introduction of invasive species. We've already eliminated numerous species and pushed many more to the brink of extinction. If this continues, the fossil record will show a sharp decline in biodiversity beginning in the 19th or 20th century, concentrated in particular groups like large mammals, amphibians, and species restricted to islands or other isolated habitats. Would this extinction be recognizable as anthropogenic millions of years in the future? The pattern might offer clues. Natural mass extinctions typically affect marine and terrestrial ecosystems similarly, since the causes, volcanic emissions, climate change, ocean chemistry disruption, affect the entire planet. The end Permian extinction, the worst of the Big Five, eliminated about 96% of marine species and 70% of terrestrial vertebrate species, driven by massive volcanic eruptions in Siberia that released enormous quantities of carbon dioxide and sulfur dioxide, triggering global warming, ocean acidification, and oxygen depletion in the oceans. The end Cretaceous extinction famously killed the non-avian dinosaurs, but also eliminated about 75% of all species, caused by the combined effects of an asteroid impact and ongoing volcanic activity in India. The human-caused 6th extinction has a different pattern. We're disproportionately affecting large animals, particularly those with small populations or restricted ranges, and we're impacting certain ecosystems more than others. Tropical forests and coral reefs are especially hard hit. Marine species are affected, but not as severely as many terrestrial species, at least not yet. The selectivity of extinction reflects the nature of our impacts. Habitat destruction, hunting, and climate change affect different species differently, depending on their ecology and life history. This selectivity might be detectable in the fossil record as an unusual pattern, species disappearing not because of a single catastrophic event, but because of complex, interconnected pressures that varied by region and ecosystem. However, interpreting extinction patterns is difficult even for well-studied ancient events. The fossil record doesn't preserve all species equally. Organisms with hard parts like shells or bones are more likely to fossilize, and the temporal resolution isn't always precise enough to determine whether extinctions happen suddenly or over thousands of years. For some of the Big Five extinctions, debate continues about the exact timing and causes, with evidence supporting multiple contributing factors and complex interactions between climate, ocean chemistry, and biological systems. If we struggle to fully understand these natural extinctions with millions of years of subsequent research, could we confidently identify an extinction caused by a prior civilization? One distinguishing feature might be the combination of extinction with other signatures. If a sharp drop in biodiversity coincided with rapid climate change, unusual isotope excursions, elevated heavy metal concentrations, and the appearance of synthetic organic compounds in sediments, the combined pattern would be suggestive of industrial activity, even if each individual marker could have natural explanations. The consilience of multiple independent lines of evidence, all pointing to a brief period of unusual environmental disruption, would be harder to dismiss as coincidence or natural variability. Another consideration is the recovery pattern after extinction. Natural mass extinctions are typically followed by long periods of low diversity and then gradual radiation of surviving lineages into newly available ecological niches. The recovery takes millions of years, with ecosystems reorganizing and new dominant groups emerging. If a prior civilization caused an extinction and then themselves went extinct or declined to pre-industrial levels, the recovery pattern might be similar to natural extinctions, with biological diversification filling empty niches over time. But if the civilization survived its own ecological crisis and continued to shape ecosystems, the recovery pattern might be unusual, showing continued suppression of diversity in certain groups or continued dominance of species the civilization favored or created. There's a sobering implication here. If mass extinctions can be caused by industrial civilizations, and if such extinctions are difficult to distinguish from natural ones in the geological record, then we cannot rule out the possibility that some of Earth's ancient extinctions had technological causes. This doesn't mean we should reinterpret every extinction as evidence of lost civilizations. The known natural causes are generally sufficient to explain the patterns we observe. But it does mean we should maintain intellectual humility about the completeness of our explanations, especially for extinctions where the causes are still debated or where multiple factors seem to have contributed. The current sixth extinction also serves as a reminder of the responsibility that comes with technological power. We're demonstrating that industrial civilizations can profoundly alter planetary ecosystems, potentially to the point of triggering mass extinctions that will be visible in the fossil record for hundreds of millions of years. This geological legacy will outlast our cities, our books, our art, perhaps even our species. Future geologists studying this time period will see a world transformed, ecosystems simplified, diversity diminished, all compressed into a thin stratigraphic layer, marking the brief industrial pulse of a species that remade the world, and then, perhaps, paid the price for doing so without sufficient wisdom or restraint. Would this extinction be recognizable as anthropogenic millions of years in the future? The pattern might offer clues. Natural mass extinctions typically affect marine and terrestrial ecosystems. Similarly, since the causes, volcanic emissions, climate change, ocean chemistry disruption, affect the entire planet. The end Permian extinction, the worst of the Big Five, eliminated about 96% of marine species and 70% of terrestrial vertebrate species, driven by massive volcanic eruptions in Siberia that released enormous quantities of carbon dioxide and sulfur dioxide, triggering global warming, ocean acidification, and oxygen depletion in the oceans. The end Cretaceous extinction famously killed the non-avian dinosaurs, but also eliminated about 75% of all species, caused by the combined effects of an asteroid impact and ongoing volcanic activity in India. The human-caused sixth extinction has a different pattern. We're disproportionately affecting large animals, particularly those with small populations or restricted ranges, and we're impacting certain ecosystems more than others. Tropical forests and coral reefs are especially hard hit. Marine species are affected, but not as severely as many terrestrial species, at least not yet. The selectivity of extinction reflects the nature of our impacts. Habitat destruction, hunting, and climate change affect different species differently, depending on their ecology and life history. This selectivity might be detectable in the fossil record as an unusual pattern, species disappearing not because of a single catastrophic event, but because of complex, interconnected pressures that varied by region and ecosystem. However, interpreting extinction patterns is difficult even for well-studied ancient events. The fossil record doesn't preserve all species equally. Organisms with hard parts like shells or bones are more likely to fossilize, and the temporal resolution isn't always precise enough to determine whether extinctions happen suddenly or over thousands of years. For some of the Big Five extinctions, debate continues about the exact timing and causes, with evidence supporting multiple contributing factors and complex interactions between climate, ocean chemistry, and biological systems. If we struggle to fully understand these natural extinctions with millions of years of subsequent research, could we confidently identify an extinction caused by a prior civilization? One distinguishing feature might be the combination of extinction with other signatures. If a sharp drop in biodiversity coincided with rapid climate change, unusual isotope excursions, elevated heavy metal concentrations, and the appearance of synthetic organic compounds in sediments, the combined pattern would be suggestive of industrial activity, even if each individual marker could have natural explanations. The consilience of multiple independent lines of evidence, all pointing to a brief period of unusual environmental disruption, would be harder to dismiss as coincidence or natural variability. Another consideration is the recovery pattern after extinction. Natural mass extinctions are typically followed by long periods of low diversity and then gradual radiation of surviving lineages into newly available ecological niches. The recovery takes millions of years, with ecosystems reorganizing and new dominant groups emerging. If a prior civilization caused an extinction and then themselves went extinct or declined to pre-industrial levels, the recovery pattern might be similar to natural extinctions, with biological diversification filling empty niches over time. But if the civilization survived its own ecological crisis and continued to shape ecosystems, the recovery pattern might be unusual, showing continued suppression of diversity in certain groups or continued dominance of species the civilization favored or created. There's a sobering implication here. If mass extinctions can be caused by industrial civilizations, and if such extinctions are difficult to distinguish from natural ones in the geological record, then we cannot rule out the possibility that some of Earth's ancient extinctions had technological causes. This doesn't mean we should reinterpret every extinction as evidence of lost civilizations. The known natural causes are generally sufficient to explain the patterns we observe. But it does mean we should maintain intellectual humility about the completeness of our explanations, especially for extinctions where the causes are still debated or where multiple factors seem to have contributed. The current sixth extinction also serves as a reminder of the responsibility that comes with technological power. We're demonstrating that industrial civilizations can profoundly alter planetary ecosystems, potentially to the point of triggering mass extinctions that will be visible in the fossil record for hundreds of millions of years. This geological legacy will outlast our cities, our books, our art, perhaps even our species. Future geologists studying this time period will see a world transformed, ecosystems simplified, diversity diminished, all compressed into a thin stratigraphic layer, marking the brief industrial pulse of a species that remade the world and then, perhaps, paid the price for doing so without sufficient wisdom or restraint. Earth's climate has fluctuated dramatically over geological time, swinging between hothouse periods with no polar ice caps and ice ages with continental glaciers covering large portions of North America and Eurasia. These climate changes are preserved in multiple archives: ice cores from Antarctica and Greenland, ocean sediment cores showing the isotopic composition of ancient seawater, growth rings in ancient trees and corals, and chemical weathering patterns in terrestrial rocks. Climate proxies allow scientists to reconstruct temperature, precipitation, atmospheric composition, and ocean circulation patterns extending back hundreds of millions of years. As we search for evidence of prior industrial civilizations, climate records offer both opportunities and challenges. Opportunities because industrial activity affects climate in detectable ways. Challenges because natural climate variability is large and sometimes shows rapid changes that might mimic industrial signatures. The physics connecting industrial activity to climate change is straightforward. Burning fossil fuels releases carbon dioxide, a greenhouse gas that traps infrared radiation and warms the atmosphere. Deforestation removes plants that would otherwise absorb carbon dioxide through photosynthesis. Agriculture releases methane from livestock and rice paddies and nitrous oxide from fertilized soils, both potent greenhouse gases. Industrial processes release various halocarbons and other chemicals that affect atmospheric chemistry and radiative balance. The combined effect of these emissions has increased atmospheric carbon dioxide from about 280 parts per million before the Industrial Revolution to over 420 parts per million today, driving global temperature increases of approximately 1.1 degrees Celsius, with more warming committed due to the lag between emissions and climate response. This warming is visible in multiple climate archives. Ice cores from Antarctica show atmospheric carbon dioxide concentrations preserved in tiny air bubbles trapped as snow compressed into ice over hundreds of thousands of years. The concentration remained between 170 and 300 parts per million for the entire 800,000-year record until the recent industrial spike. Ocean sediment cores show warming through oxygen isotope ratios in foraminifera shells, microscopic marine organisms whose calcium carbonate tests preserve the isotopic signature of the seawater they grew in, with the ratio shifting as ice sheets melt and the ocean warms. Coral growth bands show similar warming trends. Tree rings in temperature-sensitive regions show accelerated growth. The signals are globally distributed and mutually consistent. Could a prior civilization have left similar climate signals? The answer depends on how far back we look and what climate archives still exist from that time. Ice cores currently extend back only about 800,000 years for Antarctica and 125,000 years for Greenland. Ice older than that has either melted during warmer periods or been compressed and deformed so that the annual layers are no longer distinguishable. This means ice cores can't tell us about climate or atmospheric composition during most of Earth's history. They're extraordinarily valuable for understanding recent ice ages, but useless for looking at climate tens or hundreds of millions of years ago. Ocean sediment cores extend much further back, potentially covering the entire Cenozoic era, the last 66 million years since the asteroid impact that ended the Cretaceous. These cores provide lower temporal resolution than ice cores, typically averaging over thousands of years per sample rather than preserving annual layers. But they do record long-term climate trends and can detect relatively rapid climate events like the PETM. The oxygen isotope record from ocean sediments shows the long-term cooling of Earth's climate over the past 50 million years. From greenhouse conditions in the early Eocene, when crocodiles lived near the Arctic Circle, to the modern Ice Age climate, with permanent Antarctic and Greenland ice sheets. Within this long-term trend, numerous rapid climate events appear as anomalies in the record. The PETM stands out as a massive carbon release and warming event lasting about 150,000 years, with temperatures rising 5 to 8 degrees Celsius globally. Smaller but still significant warming events occurred at intervals throughout the Paleocene and Eocene. During Ice Age cycles of the past 2 to 3 million years, transitions between glacial and interglacial conditions occurred over thousands of years, driven by variations in Earth's orbit and tilt that changed the distribution of sunlight, but amplified by feedback mechanisms involving carbon dioxide, methane, ice albedo, and vegetation changes. Some of these rapid climate events show characteristics that might be confused with industrial climate change. Rapid temperature increases, carbon isotope excursions, indicating release of biologically derived carbon, and changes in ocean chemistry, including acidification. The PETM in particular has been extensively studied as a potential analogue for current climate change. Though the rate of carbon release during the PETM, though rapid geologically, was likely slower than current anthropogenic emissions. If we were examining the PETM with no prior knowledge of its cause, could we determine whether it was natural or technological? Probably not with certainty, though the duration, about 150,000 years, seems longer than we'd expect for an industrial civilization's carbon pulse, unless the civilization was much longer lived than ours, or unless their emissions triggered long-lasting feedback mechanisms. The challenge of distinguishing anthropogenic from natural climate change in deep time is fundamentally about pattern recognition and consilience with other evidence. A rapid warming event by itself doesn't indicate civilization, but a warming event coinciding with unusual isotopic signatures, elevated heavy metals, synthetic organic compounds, and an extinction pulse might. The combination becomes more compelling than any single marker alone. This is why the Silurian hypothesis emphasizes looking for multiple independent signatures rather than relying on one type of evidence. There's another consideration. Not all industrial civilizations would necessarily cause dramatic climate change. A civilization that developed renewable energy, nuclear fusion, or highly efficient energy systems early in their technological development might avoid large-scale fossil fuel combustion. A civilization with different biology might have lower energy needs or different waste products. A civilization aware of climate feedbacks might deliberately limit emissions or actively remove carbon from the atmosphere. The absence of a clear climate signal wouldn't prove the absence of civilization. It might just mean they were more careful than we've been. As you let these thoughts settle, consider the deep irony. We're searching for evidence of past civilizations by looking at the damage they might have inflicted on their environment. And we're doing this while demonstrating exactly how an industrial civilization creates such damage. We're writing our own geological signature, even as we wonder whether others wrote similar messages in more ancient stone. The search for prior civilizations is also a mirror, reflecting back our own choices and impacts, forcing us to see ourselves as future geologists might see us. A brief pulse of industrial activity, a climatic anomaly, a thin layer in the rock record marked by plastic and extinction and isotopic strangeness, a civilization that reached for the stars while struggling to understand and protect the world beneath its feet. At this point in our exploration, you might be wondering, if prior industrial civilizations had existed on Earth, wouldn't we have found evidence by now? We've examined rocks from every period of Earth's history, collected fossils from around the world, measured isotopes and elements with extraordinary precision, and built detailed reconstructions of ancient climates and ecosystems. Surely, if another civilization had existed, even millions of years ago, we would have noticed something unusual, some anomaly that couldn't be explained by natural processes alone. The apparent absence of such evidence seems like a strong argument against the hypothesis. But the logic of negative evidence is subtle and requires careful examination. Absence of evidence is not evidence of absence. This principle is fundamental to scientific reasoning but often misunderstood. To understand it, consider what it takes to prove something doesn't exist. If you're searching for your keys in your house, checking the kitchen table and not finding them there, doesn't prove the keys don't exist. It just proves they're not on the kitchen table. To prove the keys aren't anywhere in the house, you'd need to search every possible location thoroughly. Even then, you might miss them if they fell behind furniture or into an unexpected place. The burden of negative proof is extraordinarily high, requiring comprehensive, exhaustive searching. The geological record is not comprehensively searched. It's sampled opportunistically, driven by practical considerations about where rocks are accessible, what time periods are of interest for particular research questions, and what analytical techniques are available and affordable. Much of Earth's surface is covered by ocean, vegetation, or recent sediments, making older rocks inaccessible without expensive drilling. Large portions of the continental crust have been heavily metamorphosed or eroded, destroying or transforming whatever sedimentary records originally existed. Tectonic subduction has consumed vast quantities of seafloor, carrying ancient sediments into Earth's mantle, where they're melted and recycled. The rocks we can study represent a biased, incomplete sample of Earth's history. Moreover, most geological and paleontological research isn't looking for evidence of prior civilizations. Studies focus on natural processes, the evolution of life, the causes of mass extinctions, the timing and mechanisms of climate change, the formation of ore deposits, the reconstruction of ancient environments. Analytical techniques are optimized for these questions. Geochemists measuring isotopes are typically interested in natural fractionation processes, not looking for anomalies that might indicate technological activity. Paleontologists studying fossils aren't examining sediments for synthetic organic compounds. The absence of reported evidence for prior civilizations might simply reflect the fact that nobody's been looking specifically for such evidence with appropriate methods. This is analogous to the famous streetlight effect, in which a person searching for lost keys looks only under the streetlight because that's where the light is best. Even if the keys were actually lost elsewhere in the darkness, scientific research gravitates toward questions that seem answerable with available techniques and that fit within existing theoretical frameworks. The question of prior civilizations has seemed like science fiction, not serious science, so it hasn't motivated dedicated research programs or the development of specialized detection methods. This is starting to change. The Schmidt and Frank paper on the Silurian Hypothesis has sparked some interest in looking more carefully for unusual signatures in the geological record, but the work is just beginning. There's also the question of what we're capable of detecting with current technology and understanding. Some potential signatures might be present in rocks we've already analyzed, but we don't recognize them because we don't know what pattern to look for, or because our analytical techniques don't have sufficient sensitivity or specificity. Imagine trying to detect microplastics in rock samples before anyone conceived of synthetic polymers or developed methods to identify them. The plastics could be there, visible under a microscope, but they'd just look like small particles of unusual organic material, perhaps interesting, but not obviously meaningful. Similarly, unusual isotope ratios or element concentrations might exist in samples we've studied, but they're dismissed as measurement error or natural variability because we have no framework for interpreting them as technological signatures. The resolution of the geological record creates another layer of difficulty. As we discussed earlier, sedimentary rocks typically integrate information over thousands to hundreds of thousands of years. An industrial civilization that lasted 10,000 years, much longer than ours has existed, might be compressed into a sedimentary layer only a few centimeters thick. If that layer is mixed with surrounding sediments through biotubation, sediment-dwelling organisms mixing the upper layers of sediment, or if it's not sampled precisely because researchers took samples every 50 centimeters through the rock section and happened to miss the critical layer, the signal would be diluted or entirely missed. Finding a brief pulse in the geological record requires both luck and very high-resolution sampling. There's also the fundamental problem that we're reasoning from a sample size of 1. We know what human industrial civilization looks like and what signatures it leaves, but we don't know whether those characteristics are universal for all industrial civilizations or specific to our particular biology, history, and technological path. A different species might industrialize differently, use different energy sources, create different waste products, organize their society in ways that left different environmental footprints. We might be looking for the wrong signatures simply because we're generalizing from our own example, without recognizing how contingent our specific trajectory has been. Finally, consider the timeline. Earth has existed for 4.5 billion years. Complex animal life has existed for about 540 million years. If we restrict our search to periods when complex life existed, since we assume industrial civilizations require multicellular organisms with the potential to evolve intelligence, we're looking at roughly 12% of Earth's history. If industrial civilizations arise rarely, say with a frequency of once every 100 million years on average, and each lasts only 10,000 to 100,000 years, then the geological record might contain 5 or 6 brief industrial pulses scattered across 500 million years. Finding any one of them in the incomplete, biased, coarsely sampled geological record would be extraordinarily lucky. This doesn't prove prior civilizations existed. It just means we should be humble about claims that they didn't. The absence of recognized evidence so far tells us that either no prior civilizations existed, or they existed but left signatures we haven't detected yet. Or they existed and left signatures that have been destroyed by geological processes. Or they existed but in forms so different from ours that we wouldn't recognize their signatures even if we saw them. These possibilities are not equally likely, and most scientists would favor the first as the most parsimonious explanation. But we should acknowledge that the question remains genuinely open in ways that surprise many people when they first encounter the Silurian hypothesis and think carefully about what we can and cannot know about deep time. If we accept that the question of prior civilizations remains open, at least in principle, the next step is to identify which periods in Earth's history could plausibly have hosted industrial civilizations. Not all of Earth's history is equally promising. For most of the planet's existence, conditions were simply not suitable for complex, intelligent life capable of developing technology. By examining what requirements an industrial civilization would need, and when those requirements were met, we can narrow our search to specific windows of possibility, periods when the evidence would be most likely to exist if such civilizations arose. The first and most fundamental requirement is complex multicellular life. Industrial civilization requires organisms with sufficient complexity to develop nervous systems, sensory organs, and manipulative appendages capable of creating and using tools. Single-celled organisms, which dominated Earth for the first 3 billion years of life's existence, simply don't have the biological substrate for intelligence or technology. This eliminates roughly 2/3 of Earth's history. Immediately, we need to focus on the Phanerozoic Eon, the most recent 541 million years since the Cambrian explosion, when complex animal life diversified rapidly and filled Earth's oceans and eventually its land surfaces. The second requirement is sufficient atmospheric oxygen. Intelligence, particularly the kind that supports active, tool-using behavior, requires substantial energy metabolism. Brains are metabolically expensive, consuming about 20% of the human body's energy budget, despite being only 2% of body mass. Large, active animals with complex nervous systems need oxygen levels high enough to support aerobic metabolism at the scales required. Current atmospheric oxygen is about 21%, and it's been in the general range of 15 to 35% for most of the Phanerozoic, though with significant variations. Periods with very low oxygen, below about 15%, would make it difficult for large, metabolically active organisms to exist at all, let alone develop the energy surplus needed for complex behavior and technology. The third requirement is terrestrial habitats. While science fiction sometimes imagines aquatic civilizations, the practical requirements for industrial technology, controlled fire for metallurgy and chemistry, electrical systems that don't short-circuit, many construction materials and techniques strongly favor land-based development. We should focus on periods when terrestrial ecosystems were well established, with plants, arthropods, and vertebrates colonizing the land. This happened during the Silurian and Devonian periods, roughly 440 to 360 million years ago, and terrestrial life has been present continuously since then. The fourth consideration is the existence of suitable organisms. Industrial civilization requires not just complex life, but intelligent life with certain capabilities. Manipulative appendages, like hands or tentacles, sensory systems capable of detailed environmental perception, social structures that allow for cultural transmission of knowledge, and cognitive capabilities, including abstract reasoning, planning, and symbolic thought. On Earth, these capabilities have evolved primarily in certain vertebrate lineages, particularly primates, some birds like crows and parrots, and some cetaceans like dolphins and whales, and to a lesser extent in some invertebrates like octopuses. But intelligence is not inevitable. Most evolutionary lineages don't develop it because it's metabolically expensive and often not the best solution to survival challenges. Given these requirements, we can identify the most promising windows for prior civilizations. The last 66 million years, the Cenozoic era, seems particularly promising because mammals diversified during this period and many lineages evolved increased brain sizes and cognitive capabilities. Before humans, there were other intelligent mammals with manipulative capabilities, extinct primates for instance, though none that we know of approached human-level technology. The Mesozoic era, the age of dinosaurs from 252 to 66 million years ago, is intriguing. Dinosaurs included some species with relatively large brains for their body size and potentially complex social behaviors. Some theropod dinosaurs, the group that includes tyrannosaurs and eventually evolved into birds, had grasping hands with flexible fingers. Could a lineage of intelligent, dexterous dinosaurs have existed and developed technology? It seems unlikely based on what we know of dinosaur paleontology, but our knowledge is limited by the incompleteness of the fossil record. We have fossils from perhaps 1% of dinosaur species, and we know nothing about the behavior or cognition of most species. A brief flourishing of intelligent, technological dinosaurs during the Cretaceous, lasting perhaps 100,000 years before they went extinct or abandoned technology, would leave almost no direct fossil evidence and would be extraordinarily difficult to detect in rocks 100 million years old. The idea strains credulity, but it's not absolutely impossible, and that distinction matters when we're thinking carefully about what we can know versus what we assume. The Paleozoic era, from 541 to 252 million years ago, is less promising in general, but includes some interesting possibilities. Early terrestrial vertebrates, amphibians, and early reptiles had relatively simple nervous systems and no obvious path toward the kind of intelligence that might lead to technology. However, the Carboniferous period around 300 million years ago saw the evolution of early amniotes, the group that includes all reptiles, birds, and mammals. And some arthropods like giant dragonflies and millipedes grew to impressive sizes in the oxygen-rich atmosphere. Could an intelligent arthropod lineage have arisen? Arthropod nervous systems are organized differently from vertebrate brains, but they can support complex behavior, as seen in modern insects and especially in octopuses, which are mollusks but show remarkable problem-solving abilities despite having decentralized nervous systems. The further back we look, the less plausible prior civilizations become, simply because the organisms present were simpler and less likely to evolve the specific combination of traits needed for technology. But plausibility is not the same as impossibility. The history of paleontology includes numerous surprises. The discovery that birds are dinosaurs, that whales evolved from terrestrial mammals, that complex eyes evolved multiple independent times, that some dinosaurs had feathers and some were warm-blooded. Life is more diverse and surprising than we often expect, and evolution explores possibilities that seem unlikely until we find them preserved in stone. If we're serious about searching for evidence of prior civilizations, we should probably focus initial efforts on the Cenozoic and perhaps the late Mesozoic, the most recent 200 million years or so, when complex terrestrial life was well established, and when some organisms existed with plausibly pre-adaptive traits for intelligence and technology. We should look particularly carefully at periods just after mass extinctions, when ecological niches opened up and evolutionary innovation accelerated, providing opportunities for new kinds of organisms to arise and explore new strategies for survival. We should examine sediments from regions where fossilization conditions were good and where the geological record is relatively complete, providing the best chance of detecting brief anomalous events. But we should also remain humble about the search. Even in the most favorable periods, detection is not guaranteed. An industrial civilization could have existed, left subtle signatures, and still escape our notice if we don't sample the right rocks at the right resolution with the right analytical techniques. The windows of possibility are open, but what might be visible through them remains uncertain, tantalizingly out of focus, inviting further investigation while resisting easy answers. The Silurian Hypothesis extends naturally beyond Earth to other worlds in our solar system, and eventually to exoplanets orbiting distant stars. If detecting prior civilizations on Earth is challenging, detecting them on other worlds is even more difficult, but the question is no less important. Several bodies in our solar system may have been habitable in the past, potentially hosting life, and however unlikely, possibly hosting technological civilizations before conditions changed, and those worlds became the barren or frozen places we observe today. The same detection principles apply, but with the added challenge that we have far less access to these worlds' geological records. Venus is perhaps the most intriguing case in our solar system. Today, Venus is hellish. Surface temperatures around 465 degrees Celsius, atmospheric pressure 90 times Earth's, clouds of sulfuric acid, and a runaway greenhouse effect that makes the planet completely inhospitable to any life we can imagine. But Venus wasn't always this way. Climate models suggest that for perhaps 2 to 3 billion years, from about 4 billion to 700 million years ago, Venus may have had liquid water oceans, moderate temperatures, and potentially habitable conditions. The planet's slower rotation and lack of a large moon to stabilize its tilt might have created different seasonal patterns than Earth. But the energy balance could have supported a clement climate, despite Venus being closer to the Sun. If Venus was habitable for billions of years, could life have arisen there? Could that life have evolved complexity and intelligence? Could a Venusian civilization have developed technology, built cities, and then perished when the planet transitioned to its current state? The scenario seems wildly speculative, but it's not physically impossible. The challenge is that Venus's current conditions have likely erased most evidence from its surface. The extreme temperatures would have destroyed any organic materials, and geological recycling through volcanism has probably resurfaced the planet within the last billion years, burying or erasing whatever surface features existed before. If a Venusian civilization left ruins, they're buried under hundreds of meters or kilometers of volcanic rock, inaccessible to current exploration. However, some evidence might persist. If Venusian civilization had existed and had developed technology, they might have altered atmospheric composition in detectable ways. Certain synthetic molecules might survive in the upper atmosphere or in minerals protected from surface conditions. If they had space capability, they might have left artifacts on other bodies in the solar system, debris on Venus's moon, if it had one, which it doesn't, or potentially on asteroids, or even on Earth, if there was ever travel between the two worlds in the deep past. These possibilities are remote, but they illustrate how the question extends beyond single worlds to entire planetary systems. Mars offers another intriguing possibility. Mars today is cold and dry, with a thin atmosphere that can't support liquid water at the surface, and with surface conditions sterilized by intense ultraviolet radiation. But Mars was very different in its early history. About 3 to 4 billion years ago, Mars had a thicker atmosphere, warmer temperatures, and liquid water flowing across its surface, carving the valleys and channels we still observe today. This wet period lasted perhaps 1 billion years, comparable to the time between life's origin on Earth and the evolution of complex multicellular organisms. If life arose on Mars during this period, it would have had a vast span of time to evolve and potentially develop complexity. Could intelligent life have arisen on Mars? Could Martians have built an industrial civilization before the planet's magnetic field failed, its atmosphere was stripped away by solar wind, and the surface became uninhabitable? The scenario is unlikely. Life on Mars, if it existed at all, probably remained microbial, but the question invites serious consideration. If Martian civilization had existed 3 billion years ago, what would we be able to detect today? Surface structures would have been eroded or buried by billions of years of wind-blown dust and occasional impacts. But subsurface artifacts might persist, protected from radiation and weathering. Chemical signatures in rocks might remain. The challenge is that we've explored only tiny fractions of Mars's surface, a few landing sites, some orbiter imaging and spectroscopy, far too little to rule out localized anomalies. The moons of the outer solar system present yet another set of possibilities. Europa, Enceladus, and Titan all have conditions that might support life, though very different from Earth's surface environment. Europa and Enceladus have subsurface oceans beneath ice shells, kept liquid by tidal heating from their parent planets. Could life exist in those dark oceans, clustered around hydrothermal vents similar to those on Earth's seafloor? Could such life develop complexity and intelligence without sunlight, without a surface, without access to fire or materials for technology? It seems unlikely but not impossible. and if civilizations could develop in such environments, detecting them would be nearly impossible with current technology. Titan, Saturn's largest moon, has a thick atmosphere and liquid methane lakes on its surface. Life on Titan would have to be radically different from Earth life, using different chemistry adapted to temperatures around -180 degrees Celsius. But chemistry is chemistry, and complex molecules can form and interact in many environments. If life exists on Titan, could it become intelligent? Could it develop technology using entirely different materials and energy sources than we employ? These questions push the boundaries of astrobiology and challenge our assumptions about what life and intelligence must look like. The search for prior civilizations extends ultimately to exoplanets, thousands of worlds orbiting other stars. We're beginning to characterize exoplanet atmospheres through transit spectroscopy, analyzing the light that filters through an exoplanet's atmosphere when it passes in front of its star from our perspective. We're looking for biosignatures, chemical indicators of life, like oxygen, methane, and other gases that might be produced by biological processes. But could we detect technosignatures, indicators of technological activity? Industrial pollution, synthetic molecules, artificial light on the night side, excess heat from cities or power generation, structures in orbit. The challenge is sensitivity. Exoplanets are extraordinarily distant, light years away, and incredibly faint compared to their stars. Detecting subtle chemical signatures or artificial structures requires observations at the limits of current technology and often beyond. If we struggle to detect a hypothetical prior civilization on Earth, where we can sample rocks directly, how much more difficult to detect one on an exoplanet, where we're limited to analyzing pixelated images and low-resolution spectra? Yet the search continues because the question is so profound. Are we alone, not just now but throughout cosmic history? Has technological intelligence arisen elsewhere, and if so, how often and under what circumstances? The question of prior civilizations on Earth is ultimately a local version of this larger cosmic question. It's about understanding how rare or common technological intelligence might be, about learning to recognize its signatures across vast spans of time and space, and about developing the humility to acknowledge how little we know and how much remains hidden in the gaps of our knowledge, in the rocks we haven't sampled, the questions we haven't asked, and the patterns we haven't yet learned to see. Having explored how we might detect prior industrial civilizations, it's worth turning the question around and asking what future geologists will find when they study the rocks being formed today. What signatures is our civilization leaving in the geological record? This question has practical importance for understanding the Anthropocene, the proposed new epoch defined by human impacts on Earth's systems, and it provides a concrete way to think about what persistence means in deep time. Our civilization is conducting a real-time experiment in geological legacy, writing messages in stone and ice that will persist long after our cities have crumbled, and our species has either evolved into something different or disappeared entirely. The most obvious signature will be the changes we've made to Earth's surface. We've moved more soil and rock through construction, mining, and agriculture than natural erosion processes move in an equivalent time. Geologists call this phenomenon human as a geomorphic agent. We've leveled mountains, filled valleys, redirected rivers, drained wetlands, and created artificial coastlines. In many regions, the top layers of soil are thoroughly mixed and homogenized by plowing, creating a distinct anthropogenic layer visible in soil profiles. Cities create their own unique deposits, layers of concrete, asphalt, brick, steel, and other construction materials mixed with trash, sewage, and industrial waste. These urban strata would be recognizable as artificial even after millions of years of burial and compression. The chemical signatures we discussed in earlier chapters will persist at varying timescales. The plastic stratum forming in current sediments should remain detectable for millions of years. Thin layers of microplastic particles distributed globally in both marine and terrestrial sediments. The spike in radioactivity from nuclear testing will be visible for tens of thousands of years through elevated plutonium-2, 3, 9, and other long-lived isotopes. The carbon isotope excursion from fossil fuel combustion will persist in carbonate rocks and organic-rich sediments, marking a brief period when isotopically light carbon flooded into the atmosphere and oceans. Elevated concentrations of heavy metals from mining and industrial emissions, particularly lead, mercury, and rare earth elements, will appear in sediment cores worldwide, concentrated in the layer corresponding to the 19th through 21st centuries. The extinction pulse we're currently causing will be visible as a sharp decline in biodiversity in the fossil record. Large mammals, particularly megafauna like elephants, rhinoceroses, and great apes, will show sudden range contractions and population crashes followed by extinction. Many bird species, especially those on islands and those with specialized habitat requirements, will disappear. Coral reefs will show a dramatic die-off, the selectivity of this extinction preferentially affecting large animals and habitat specialists, while some generalist species thrive, will mark it as unusual compared to the big five extinctions that affected ecosystems more indiscriminately. The speed of the extinction, compressed into a few centuries, will be geologically instantaneous, though the exact timing might be blurred by the limited resolution of the fossil record. Climate change will leave multiple signatures. The rapid warming of the past century and the continued warming projected for coming decades will appear in various climate proxies. Oxygen isotope ratios in ice cores and marine sediments, changes in pollen assemblages in lake sediments, indicating shifts in vegetation zones, growth rings in corals and long-lived trees, and the elevation of snowlines and glaciers. Ocean acidification from absorbed carbon dioxide will affect the chemistry and isotopic composition of marine carbonates. Changes in precipitation patterns will alter sediment deposition rates and weathering signatures in terrestrial rocks. The combination of warming rate, carbon isotope shifts, and other chemical changes will mark this climate transition as unusual, though whether future geologists would recognize it as anthropogenic without other context is uncertain. Agricultural transformation of the landscape will leave its own signatures. The proliferation of domesticated species, visible in the fossil record and in genetic lineages distinct from wild relatives, indicates artificial selection and human control. The spread of certain crops globally, far beyond their native ranges, creates unusual biogeographic patterns. Changes in nitrogen isotope ratios in soils and sediments from synthetic fertilizer use mark a fundamental alteration of the nitrogen cycle. Soil erosion from intensive agriculture increases sediment deposition rates in rivers and coastal areas, creating unusually thick layers of fine-grained sediment. The conversion of forests to agricultural land changes pollen records and carbon storage patterns visible in sediments. Our infrastructure itself might leave surprisingly persistent traces. While most buildings and roads will decay relatively quickly, some structures will last longer. Stone monuments and foundations, especially those made of durable rock like granite, might persist as recognizable ruins for hundreds of thousands of years. Deep mines create voids in bedrock that will eventually collapse, but might leave distinctive brecciated zones recognizable in cross-section. Tunnels for subways and utilities create unusual subsurface structures. Dams create artificial lakes that trap sediment, preserving detailed records of the period when the dam existed. Landfills create concentrated deposits of unusual materials that might be recognizable even after millions of years of burial and transformation. Some of our most lasting legacies might be things we didn't intend to create. The redistribution of species, intentional through agriculture and pets, unintentional through invasive species, creates biogeographic patterns that will take millions of years of evolution and continental drift to fully erase. The mixing of biota from different continents, visible already in genetic records, represents a kind of biological homogenization that reverses patterns established over hundreds of millions of years of continental separation. The creation of entirely new substances, synthetic chemicals, alloys, ceramics, might have trace persistence even after the original. Compounds degrade, leaving unusual elemental distributions or isotopic patterns. Future technologies might create their own signatures. If we develop widespread fusion power, we'll create unusual concentrations of fusion products and might alter helium isotope ratios. If we engage in large-scale geoengineering to counteract climate change, we might leave signatures from stratospheric aerosol injection or ocean alkalinization. If we eventually establish permanent settlements in space, we'll leave artifacts beyond Earth, where preservation conditions are much more favorable than on our geologically active planet. Time capsules on the Moon, whether intentional like the Apollo mission's equipment or hypothetical future monuments, would remain essentially unchanged for billions of years. The complete picture of our geological legacy includes aspects both profound and troubling. We're demonstrating that industrial civilizations leave clear, multifaceted signatures that should be detectable for millions of years, even if the exact nature of the civilization that created them becomes obscure. This is valuable data for the Silurian Hypothesis. It establishes what kinds of signatures persist and on what timescales, providing calibration for searches through deeper time, but it's also sobering. We're showing that the environmental costs of industrialization, extinctions, climate change, chemical pollution can be severe and long-lasting, written permanently into the planet's history. This raises profound ethical questions about our responsibility to deep time. Most human ethical systems focus on relatively short timescales. Our own lives, our children's lives, perhaps a few generations forward. But our actions are creating consequences that will persist for thousands to millions of years, far beyond any human moral community we can imagine or relate to. Do we owe anything to these distant futures? Should we care that geologists 10 million years from now will see an anomalous layer in the rocks and recognize it as evidence of a brief, intense civilization that altered the planet and then perhaps vanished? These questions have no easy answers, but they're worth contemplating as you settle deeper into the night, your thoughts drifting across vast timescales, connecting your momentary existence to the long arc of geological history. As we come to the end of this exploration, let's return to where we began, the question of whether we're the first industrial civilization on Earth. We've examined the nature of deep time, the mechanisms of geological preservation, the potential signatures that industrial civilizations might leave, and the challenges of detecting those signatures millions of years later. We've confronted the incompleteness of the fossil record, the limits of our sampling and analysis, and the difficulty of distinguishing technological signatures from natural phenomena. We've explored windows of possibility in Earth's history when prior civilizations might have existed, and we've considered what our own civilization will leave behind for future investigators. What can we conclude? The honest answer is that we cannot conclude with certainty either way. We have no positive evidence for prior industrial civilizations on Earth, no unambiguous signatures that demand a technological explanation, no artifacts or ruins that clearly predate human evolution. The simplest explanation for this absence of evidence is that no such civilizations existed, that we are indeed the first and only industrial civilization Earth has produced in its 4.5 billion year history. This explanation fits with our understanding of evolution as contingent and path-dependent, with intelligence and technology as rare outcomes that required specific sequences of evolutionary innovations and fortunate circumstances. It fits with the apparent rarity of intelligent life in the cosmos. The Fermi paradox's observation that we don't see evidence of other technological civilizations in our galaxy despite searching for decades. But absence of evidence is not evidence of absence, and the possibility remains genuinely open that prior civilizations existed and left signatures we haven't detected yet, or that have been erased by geological processes. The time frame is so vast, the sampling so incomplete, and the resolution so coarse that we cannot rule out brief industrial pulses compressed into thin stratigraphic layers we haven't examined or couldn't distinguish from natural variations. This doesn't mean we should embrace speculation or entertain claims without evidence. It means we should maintain intellectual humility about what we know and don't know, acknowledging that our understanding of Earth's deep history, though impressive in many ways, remains incomplete and subject to revision as we develop better techniques and ask better questions. The value of the Silurian hypothesis isn't really about proving or disproving the existence of prior civilizations. Most scientists, if pressed, would say such civilizations probably didn't exist, and that's a reasonable position given available evidence. The value is in the perspective it provides. Thinking seriously about this question forces us to confront the nature of evidence, the limits of knowledge, and the strange properties of deep time. It encourages us to think about ourselves not as the culmination of Earth's history, the inevitable end point toward which evolution was always progressing, but as one contingent outcome among many possibilities, a brief experiment in industrial civilization whose long-term success or failure remains uncertain. Deep time is humbling in ways that are difficult to fully internalize. When you really try to grasp the span of Earth's history, the billions of years during which our planet existed without us, the hundreds of millions of years of complex life before any human walked or thought or built, you realize how peripheral we are to the broader story. We're newcomers, late arrivals who've been here for the blink of an eye, and whose future is measured in timespans that are vanishingly small compared to the ages that came before. The dinosaurs dominated terrestrial ecosystems for 165 million years. Our species has existed for 300,000 years, and our industrial civilization for just 250 years. We've barely begun, and yet we're already reshaping the planet in ways that will echo through millions of years of future geology. This perspective doesn't diminish human achievement or make our lives meaningless. Rather, it contextualizes our importance. We matter to ourselves, to our communities, to the ecosystems we're part of and responsible for. Our thoughts, feelings, creations, and relationships have real value and meaning within the human sphere. But the universe doesn't center on us. Earth's history doesn't build toward us as its goal. We're one form of complex pattern making that matter has discovered how to do on this particular planet during this particular epoch. Impressive and interesting, but not cosmically privileged. Other patterns existed before us and will exist after us. Some biological, some geological, some perhaps technological, if other intelligences arise here or elsewhere. The question of prior civilizations touches something deep in human psychology, our need to know our place in the larger order of things, our desire to understand whether we're unique or merely one instance of a more general phenomenon. It connects to our myths about lost civilizations, Atlantis and Lemuria, and to modern speculation about ancient astronauts and mysterious archaeological anomalies. But the Silurian hypothesis differs from these pseudo-scientific narratives in crucial ways. It doesn't claim hidden knowledge or conspiracy theories. It doesn't invoke the supernatural or violation of known physics. It simply asks a careful, methodological question about what we could detect with scientific tools and what conclusions are warranted by the available evidence. In doing so, it models good scientific thinking, taking a speculative question seriously, working out what predictions it makes, examining what evidence would be relevant, acknowledging uncertainties and limitations, and arriving at provisional conclusions subject to revision. This is how science progresses, not through absolute certainties, but through increasingly refined understanding, built on careful observation, rigorous analysis, and willingness to follow evidence wherever it leads, while maintaining skepticism about extraordinary claims that lack extraordinary evidence. As you let these thoughts settle, here on Whispering Universes, allow yourself to drift backward through time. Imagine the long procession of ages, the Cenozoic with its mammals and ice ages, the Mesozoic with its dinosaurs and flowering plants, the Paleozoic with its strange marine arthropods and early terrestrial life, the Proterozoic with its algae and bacteria slowly oxygenating the atmosphere, the Archean with its stromatolites and hot alien seas. Imagine all of Earth's history compressed into a single day, with you existing in the final fraction of a second before midnight. Feel the vastness of time that came before, the unimaginable span of ages when continents drifted, mountains rose and eroded, life evolved and diversified, and went extinct and radiated again in endless cycles. In this vast sweep of time, could another civilization have arisen and fallen? Could there have been others who looked up at the stars and wondered about their place in the cosmos, who developed science and technology, who struggled with the same questions of meaning and purpose and mortality that we struggle with? We don't know. The rocks are silent, or perhaps they're speaking in a language we haven't fully learned to understand. The answer might be written there in the sediments, in isotope ratios, and chemical signatures and patterns we haven't recognized yet. Or the answer might be simply that we're first, alone in this planet's history, carrying the weight of being the only species that knows it will die, that understands deep time, that can ask these questions at all. Either answer is profound. If we're first, we bear a special responsibility for stewardship of this planet and its life, knowing that billions of years of evolution culminated in intelligence, and that we might represent consciousness's only chance in Earth's remaining few billion years before the sun's aging renders the planet uninhabitable. If we're not first, if others came before and left barely a whisper in the rocks, then we know that technological civilization is not necessarily permanent, that intelligence doesn't guarantee long-term survival, that the industrial pulse we're living through might be brief, and that what we leave behind might be little more than a thin layer of plastic and extinction and isotopic anomaly, puzzling to whatever intelligence might investigate it millions of years hence. The question connects ultimately to the most fundamental questions we can ask. Who are we? Where do we come from? Where are we going? These questions don't have final answers, but asking them transforms how we see ourselves and our place in the cosmos. The Silurian Hypothesis invites us to think across geological timescales, to recognize our position in deep time, to understand that our moment is brief and precious precisely because it is brief, and to consider what legacy we want to leave in the rocks forming beneath our feet right now. Let your breathing slow. Let the boundaries between past and present soften. The deep past flows into this moment, and this moment flows into the deep future. All times are connected through the continuous transformation of matter and energy, the cycle of life and death and rebirth that plays out across millions and billions of years. You're part of this flow, a temporary pattern in the flux, aware and wondering and contemplating mysteries that extend far beyond any individual life or civilization. Perhaps we're first. Perhaps we're not. The question remains open, inviting further investigation, while reminding us that some things remain uncertain, that the universe preserves its secrets better than we'd like, and that the appropriate response to vast unknowns is not anxiety, but wonder. Wonder at the scale of time, at the complexity of Earth's history, at the fact that matter organized itself into patterns capable of asking these questions at all. Sleep peacefully tonight, knowing you're part of a story so much larger than yourself, a story written in stone and ice, in DNA and fossils, in the chemical cycles that connect all life to the planet and to deep time. Dream deeply, and perhaps in your dreams, you'll glimpse those vanished ages, those alternative possibilities, those strange civilizations that might have risen and fallen in Earth's ancient past. Dream gently, and let the currents of time carry you toward rest, toward renewal, toward tomorrow when you'll wake and continue adding your small but meaningful contribution to the ongoing story of life on this ancient, patient world. Thank you for joining this exploration here on Whispering Universes. Remember to like and subscribe if you'd like more journeys into deep time and cosmic questions. Until we meet again among the stars and stones, sleep well and let the mysteries of deep time fill your dreams with wonder rather than worry. We're all travelers through time, after all, moving forward at 1 second per second, leaving traces that will someday be stones for others to read and wonder about. Make them traces worth leaving. Good night.